Hello there, this is another look at trying to see how acceleration, velocity and displacement sort of combine into I don't know, a system of equations, and that's what we're trying to find today. We're looking at what are called the SUVAT equations. I don't know what happened there. So the SUVAT equations, that's me writing out SUVAT, which I probably will do in the exam questions and even the exercises as well. Quite often I start a question writing out SUVAT. And S stands for displacement. Now it's a bit weird because up to now we've been using X, but for some strange reason we always used S for displacement here. U is described as the initial velocity of an object. Initial velocity. V is described as the final velocity. And you can see why v is obviously velocity, and therefore the one before it, the initial velocity, is u. So that's the only reason we use that. A is obviously the acceleration, and t is the time taken for something to happen. And these letters are very, very commonly used. And in the past we've used, of course, x, v, and a, and you go from x to v by differentiating. And likewise, you can get from the velocity to the acceleration by differentiating again. If you go the other way, that's usually integration. And we've seen how that works as well. And this is a common question, but this works with what you describe as variable acceleration. So the acceleration is, if you like, a formula in its own right. But whereas these can work only with constant acceleration. And that's what the purpose of today's lesson is to try to derive what we describe as the SUVAT equations. We're going to try and prove them, if you like. These are actually the 5 SUVAT equations, and in physics very often they only present 4 of them, and this what I would say is the 4th one here, and it's very often missing in their list. But I think vaguely remember when I was doing this and learning this many moons ago, I only got taught these 4 and effectively needed to work out this 5th one for myself, but it's useful to know all 5. So a little start just to see what we remember from what we did last time. Now this again is going to be for variable acceleration. This is what we were playing around with last time. So this is going to be useful for what I'm going to do in a bit, but very quickly we'll be moving away from it. And its acceleration, I know, is variable because it's got an equation. It says a equals 2 minus 3t squared. And you'll notice as t changes, so does the acceleration. So the acceleration is going to change according to time. So a particle is moving in a straight line. Its acceleration is given by this equation. Given that its velocity at t equals 0 is 4.2, find an equation for the velocity. Okay, then, well, I already have highlighted this xva idea. I've got the a, so I can go upwards by integration. And so I'm going to write that v equals the integral of a dt. I've got to integrate the acceleration. And what is the acceleration? The acceleration was this 2 minus 3t squared. And so what do? Well, add the power and divide by the new power. So 2t, well, again a t. This becomes 3t cubed over 3, or just t cubed. And I suppose I should put a v at the front. I should write plus c at the end. It tells me, though, that t equals 0. Tells me t equals 0 when v equals 4.2. So presumably I can just type those in. 4.2. The lovely thing about this is you'll notice when that equals 0, disappears. So c is just 4.2, and my final equation then is 2t minus t cubed plus 4.2. And that's, again, you'll notice it's variable velocity. It changes over time. And now it's not uncommon to now have to do this next step as well. I've been asked now to find the displacement, the final step, if you like, from it, given its initial displacement from point A is 14 meters. Well, that basically tells me t equals 0. It's initial, you see. It's x is 14. Find the equation for the displacement of a at time t. Well, again, I go back to this idea that x is the integral of v dt, which is the integral of 2t minus t cubed. It's this thing I just found, you see, plus 4.2. We saw a lot of this in the last exercise. And what's this mean? Well, this means I get 2t squared over 2, t squared, t to the 4 over 4, so it's minus a quarter of t to the 4, plus 4.2t plus a different constant. Technically, I should write constant 1, constant 1, constant 2 now. And if I do this, I can now use my information here because I know now that x is this. So I can just write 14. Well, that disappears, that disappears, that disappears, this disappears. So effectively, C2 is 14. That's a very nice equation then. It's relatively easy to do. It's t squared minus a quarter t to the 4 plus 4.2t plus 14. And hopefully my answers are agreeing with that. Yeah, that one does. And that has got a slight error in as much that it should say plus there. I've obviously typed that in wrong. But you get that. Everything else has worked. Everything agrees. Prove that if the acceleration a is constant. Oh, right. So this time it's going to be constant and the initial velocity is u. Okay, so we're back to using our ideas. But now, when last time I wrote out my x, my v and my a, and I said, well, we could work our way upwards, I had a formula for a, but I integrated it. Now, my formula now is just that a is constant. A equals k, if you like, or a equals some number. So effectively, I'm just going to call it a. And so when I integrate a, remember, v will be the integral of a dt. Now, when I integrate a constant, it will just add a t, or like we did last time. We integrated 4.2 just now on the last expression, and it became 4.2t. So this simply becomes a t. Oh, don't forget my constant. V equals at plus c. And it does tell me the initial velocity is u. Well, that means that initially t equals 0, that v, the velocity is u. So I can chuck this in. I can say v, which is u. Sorry, that was make a mistake, silly thing. V is u equals a times t. Well, t is 0. So that's a times 0 plus c. And anything times 0 is 0. So therefore my constant now, my c is u. And therefore I get this equation, v equals, well, at plus u, I suppose. But everyone always writes this, v equals u plus at. This is actually one of the equations which I need to know. And we found it using integration. And it says, now find the displacement. Okay, so we do the same thing. From the starting point, well, that is basically saying t equals 0, x is 0 as well. Okay, so we have to integrate this again. So we have to get our x, we have to integrate our v with respect to t. That's what we always do. But now I've got a formula for v equals u plus at dt. And if you integrate u, well, again, it hasn't got a t on at the moment, but it will gain one. It will be ut. I will I add a power and divide by the power, plus a new constant, which again, technically I should write C1's there, and therefore this is C2. Oh, hang on a bit. I suppose I know x is 0 and t is 0, so this becomes 0 equals 0 plus 0, and you quickly realize C2 is nothing. So x equals ut. Now, again, usually we write this as a half at squared. And again, normally we tend to write s at the front instead, as I did mention that before. And so this is our formula, s equals ut plus a half at squared. Note those two equations came from old maths from chapter 19, but very useful instead. Using algebra, it says, okay, we had these two equations. Now, it doesn't tell me, well, this one I just proved. This one I haven't proven at all. They've just told me it. But it says I can use them. Okay, so I'm going to use them to derive an equation for v squared. Well, I've only got v there. I've got v there as well. I've got a u there. I tell you what I'm tempted to do. I'm tempted to get rid of, well, it doesn't have the t here. That, I suppose, is the key. it says give this in terms of u, a, and s. There's no t. So for the first one, I need to write that as t equals. So it starts off like that. I can write v minus u equals at, and therefore v minus u divided by the a equals t. That's my t equals. And then I can substitute that into here. S equals a half. What's it say? Is u plus v times by the t, but I now know what t is. What's that? S equals a half of u plus v times by, what's that, v minus u over a. And you'll notice what I've done is v minus u over a is just this t thing at the end. Well, I suppose I've got to multiply this out. So let's, well, I'll tell you what I want to do as well. I want to get rid of these fractions. So I want to move the a onto the other side and move the 2 onto the other side. So if I do that, I reckon I get 2as equals u plus v times by v minus u. Let's multiply that out. I get u times the v, so that's u v. Got to be careful here to make sure the u's and the v's look different. Minus u squared plus a v squared, and then minus a uv. That's interesting. The uv's cancel, you can see that. And that allows me then to say v squared, move the u squared over there, u squared plus 2as. And this is indeed one of my equations. So we've managed to prove a few now. And the third way is to use graphs. So now the graphs argument is basically to look at a graph like this, and you can see my graph coming up here. And it's just to use, if you like, y equals mx plus c. And if y equals mx plus c, let's just see what I can do. Well, what is my y? My y is my v. You can see it doesn't say a y-axis, it says v-axis. V equals, what's my gradient? Well, you can see it's found these 2 points here. It says after t seconds, the speed has gone from u up to v. I see this is the initial velocity, this is the final velocity, what they've talked about before. And if that is my initial velocity, and that is my final velocity, you can see, take one away from the other, v minus u is how much it's gone up. And you might remember, I don't know, I've seen people talk about the change in y. You divide it by the change in x, and that gives you the gradient. However you do it, effectively, in this case, it's v minus u over t. How far does it go across? So v equals, that's my gradient. So it's slightly weird here. I've got a v here. Oh, I know why, of course. Basically what's going on here is when you find a gradient of a velocity time graph, you might recall that the gradient is the acceleration. So when I say y equals mx plus c, that is true, but I don't need it. Really, all I'm doing is I'm saying, well, the gradient of a velocity time graph is the acceleration. And we know it's v minus u over t. So if I move the t over, I get at equals v minus u. Move the u over, v equals u plus at. I think it was one of the equations I got before, wasn't it? And it's certainly the equation they wanted me to get here. Oh, this last one, interestingly, this is one of the equations which we use on the last question, but we never actually proved. So how are we going to, it says area under a graph. Well, straight away, you notice area under the graph is, well, it's a trapezium. So it's the distance. It's saying it's the distance. You might recall from GCSE that distance under the graph is, area under the graph is the distance travelled. So it's this height here, which is obviously u. This height here, which is obviously v. And you're meant to half it and times by the difference in distance in between, which is t. In fact, that's that formula already. And that was just by finding this area under a graph and knowing that the area under the graph is the distance travelled, or if you like, the s. This was really just saying on the velocity time graph, if we know the gradient, that's the acceleration. And that's how that all came about. And so we've ended up with all these equations. And on exercise 20a, we go through these equations and we basically play around with them. But this was a question about proof. Exercise 20b is using it. All the best.